Here we have a special circuit where we have a battery connected to 3 resistors, but the 3 resistors are on different branches of the circuit. We call this circuit a parallel circuit because the parallel branches provide an alternative route for the electricity to get back to the battery. Very much like 2 roads going in one direction, you can go one road or the other road. The 2 roads are said to be in parallel. Well, in this circuit here, we say that the 3 resistors are in parallel. Now you may have noticed from the resistors they have the same colour code on them because they are all the same value of resistance. So let's see what happens when we join up the circuit. We'll join up the first one. And you can see that it's going to take a current of 0.9 amps from the battery. The current doesn't split up because it's got nowhere else to go. So the 0.90 amps leaving the battery is exactly equal to the current flowing through that top resistor. Let's join up the second branch. Now in this case the current has got an alternative way to go. But did you notice when we added that second resistor branch in, which is in parallel, the current from the battery increased. And because the resistors are same, each resistor must take the same current because they are connected across the same battery potential. And we'll show you that in a minute. Finally, let's look at the third branch. And you can see because it's an identical resistor, it's going to draw the same current from the battery, which means overall you're going to have more current from the battery. So it seems to be the first conclusion we have here is when you add resistors in parallel, you're effectively reducing the resistance of the circuit. When you reduce the resistance of the circuit, the current leaving the battery increases. And you'll know also there that the fact that we have 3 identical resistors, so the current leaving the battery, 2.70 amps, will be split 3 identical ways, only because we've got 3 identical resistors. So 2.70 divided by 3 gives you 0.90 amps. Now what's the potential difference across these resistors? Well, if we look at our voltmeter, we can take the potential difference across the top branch. And the potential difference across the top branch is 9 volts. That's exactly the same as the potential difference across the terminals of the battery, 9 volts. But the key thing here to remember is that if we have a potential difference across the top of that circuit there between those 2 points, it will be exactly the same as the potential difference across this branch, 9 volts. Which will be exactly the same potential difference across this branch because these points of the branches are connected to the terminals of the battery. So you will get 9 volts across each of the branches. And just to check the last one, 9 volts and 9 volts. Which means of course that the potential difference across each resistor is going to be the same. So the potential difference across the bottom resistor is 9 volts. The middle one must be 9 volts and this one here must be 9 volts. So we know then that if the potential difference across the resistor is 9 volts and the current passing through it is 0.90 amps, we can do a wee bit of Ohm's law here, and resistance R is equal to V divided by I, so it's 9 volts divided by 0.90 amps, and we're going to get an answer of 10. So the resistance must be 10 ohms each. So to recap this circuit, it's a parallel circuit. And what happens, the more branches we have in parallel connected to the battery at the top, then the more current will be drawn from the circuit. And the current drawn from the circuit will be split in equal ways if the 3 resistors are exactly the same. And in a minute we'll look at 3 different resistors and see what happens. The other thing to note is that the potential difference across each branch is going to be exactly the same. So 9 volts across that branch, 9 volts across this branch, and 9 volts across the other branch, which is exactly the same as the potential difference across the branch containing the battery. Here are 3 Non-identical resistors connected across the terminals of a 9-volt battery. It's a parallel circuit and resistors are arranged in parallel. How do we know they're parallel? Well, we can see that each branch offers an alternative route for the current to get back to the battery. Just the same way as you've got these two alternative roads or a bypass road. So we have 3 resistors in parallel. Now let's join up the resistance branches one at a time. The first branch, we can see we're drawing 0.30 amps from the battery. The current has nowhere else to go, so we're going to have 0.30 amps through the first or the top branch resistor. If we connect up the second one, we see that the current from the battery has increased, which tells us if you connect 2 resistors in parallel, you're reducing the overall resistance of the circuit, therefore increasing the current which is going to flow out the battery into the circuit. Another thing to notice here is that the current in the top branch is double the current in the middle branch. Now that must mean that the resistor and the top branch must be half the resistance of the bottom branch. It's offering less resistance because more current is going through it. Let's join up the third one. Once again, the current leaving the battery has increased, which tells us that the more resistors you add in parallel, therefore the more current you're taking from the battery, which means the overall resistance of the circuit has decreased. Now look at the currents now. Now from that we can see that in the top branch we have 0.30 amps going through the resistor, in the middle branch 0.15 amps going through the resistor, and in the bottom branch 0.45 amps going through the resistance. So we can see the bottom resistor or the bottom resistance branch is taking the most current. So that should be the least value of resistance. That should be the least value of resistor. If we compare each of the resistors, we can see that the top branch is taking 0.30 amps, the middle branch 0.15 amps. Therefore, we can see that the current has been halved. Therefore, the resistance between these two here, this one must be double the resistance of this one here. So let's look at the values of resistance then. Let's see if we've got them all correct. The top branch is 30 ohms, the middle branch has got a resistance value of 60 ohms, and the bottom branch 20 ohms. So you can see quite clearly how the currents are all matched up. For the 20 ohm resistor one here in the bottom branch, it is 1/3 of the resistance of the middle branch. Therefore it must take 3 times as much current, and that's quite correct. 3 times 0.15 is 0.45 amps. The top resistor is taking double the current of the middle resistor, which must mean that it's got half the value of resistance. So the resistance in the circuit, you can see, is overall reduced if we have resistors added in parallel. Now what about the voltage across each resistor? Well, we know the voltage across the battery has got to be 9 volts. And that's the same as the potential difference across this branch here, 9 volts. So across the 30 ohm branch, we have a potential difference of 9 volts. It remains the same. Across the branch of the middle resistor, we have the same potential difference. We have 9 volts. And of course, we're going to have 9 volts across the bottom branch as well. And that's all because that these branches are all connected across the same terminals of the battery. The potential difference across each resistor will be exactly the same as the potential difference across the battery. So 9 volts, 9 volts, and 9 volts. In fact, if we know the value of the potential difference across the resistor, we can calculate the current in the branch. So for example, if we've got the top resistor here, we know the potential difference has got to be 9 volts. And we know that the resistance is 30 ohms, so 9 divided by 30 is going to give you a current of 0.30 amps by Ohm's law. So that's the basis of an electric circuit. But what we want to try and find out now is the combined resistance of this circuit here, because we know the current flowing in that circuit leaving the battery is 0.90 amps. And we know the potential difference of the battery, or the EMF as we call it, is 9 volts as well. So using Ohm's law, the total resistance that circuit feels is going to be 9 volts divided by 0.90 amps, which is 10 ohms. So the combined resistance of 30 ohms, 60 ohms and 20 ohms in parallel is in fact 10 ohms. Let's see how we can work that out. Here we have a circuit theory diagram of the setup we showed in the PHET circuit simulator. We have a battery of voltage V, and we have 3 resistors connected in parallel, 3 parallel branches across the battery. The current drawing from the supply V is I amps, and in each branch the current splits up according to the value of the resistance I1, I2, I3. And the goal of this little lesson here is to find out a formula for the combined resistance of R1, R2 and R3 when they're in parallel. So we begin by the most obvious statement, and the obvious statement is that the currents which leaves the battery, current I, must be equal to the sum of all the currents in the branches. So I1 plus I2 plus I3. Now we know already that the current flowing in the circuit is just simply equal to the potential difference of the battery, the EMF of the battery, divided by the total resistance of the circuit. Now that must equal, well, in the case of I1, if we know that the voltage across this resistor here is going to be V, because the potential difference across this resistor has got to be V, across this one has got to be V, and across this one has got to be V, because they're all connected across the same terminals of the battery. So I1 will translate as V divided by R1. It's the same potential difference. I2 will be exactly the same, V divided by only the R2 resistance. And finally we have V divided by R3. Now we can see we've got a common factor here, and the common factor is quite simply V. So V divided by RT has got to be equal to, take out the V, and we're left with a very strange expression here, 1 upon R1 plus 1 upon R2 plus 1 upon R3. So we divide each side by V. V into this will cancel out to give us 1 upon RT, and that's got to be equal to 1 upon R1, because the V will cancel, plus 1 upon R2 plus 1 upon R3. So the combined resistance RT of a parallel resistance circuit is found by that formula. The total resistance can be found by saying 1 upon RT equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Let's try it out with an example. So here we have the example. Here we have the battery. We have 30 ohms, 60 ohms and 20 ohms. So according to our formula, we have 1 upon RT to find the total resistance is equal to 1 upon R1, the first resistor in the first branch, plus 1 upon R2 plus 1 upon R3. So 1 upon the total resistance of the circuit is equal to 1 upon 30 plus 1 upon 60 plus 1 upon 20. Now you can do that in your calculator, or if you're really proficient with fractions, you can say that the common denominator fraction is 60. So we can change all those fractions into 60ths. So 130 becomes 2 60ths. We just leave the 160 there. And 1/20th is the same as saying 3 60ths. So we can say that's 3 60ths there. So 1 upon RT, add up the fractions, 2 plus 1 plus 3 60ths is going to give us 6 60ths. So therefore, to find the total resistance, we just flip over and it becomes 60 divided by 6. So therefore the total resistance is equal to 10 ohms. Now we go back to our PHET arrangement. We can see that all those resistances here, 30, 60 and 20, we can effectively replace that by a 10 ohm resistor. Check out here, 9 volts divided by 10 is going to give you a current leaving the battery of 0.90 amps. So we now have an expression for the combined resistance of resistors connected in parallel. 1 upon RT equals 1 upon R1 plus 1 upon R2 plus 1 upon R3.